Block sphere breakdown. See how qubit measurement really works. Ever thought about on or off being more complicated than a light switch? What if the tiny particles that will shape our future technology can be both on and off at the same time? Or maybe neither. And get this, the simple act of looking, of just measuring them, forces an instant decision in a way that still puzzles the smartest folks out there. Ready to see things a little differently? Today, we're exploring the very strange and wonderful heart of quantum mechanics, specifically the world of qubits. These are not your typical bits of information. Nope. They exist in a sort of haze of probabilities, a world of maybes and what-ifs, right up until we try to get a look. And when we do, something called wave function collapse happens. It's a super fast, pretty dramatic jump from all those possibilities to one single solid answer. Sounds a bit like magic, doesn't it? It's definitely mind-bending. But we're going to pull back the curtain on some of that mystery. Our main tool for this? A surprisingly neat visual called the Bloch sphere. This isn't just some abstract diagram. It's a map that lets us see what's happening with a qubit. We'll get to visualize a qubit state, watch that dramatic collapse, and hopefully make one of quantum's most famous tricks a lot less confusing. So, let's get started and break down how qubit measurement really works. What is a qubit? The quantum building block. Before we can really get a handle on the Bloch sphere, we need to meet its star tenant, the qubit. You're probably familiar with classical bits, the basic units of info in our everyday computers. A classical bit is straightforward, like a reliable old light switch. It's either a 0, think off, or a 1, think on. That's all. Two states, nice and clear. Qubits, however, are playing a whole different ballgame. They're the quantum version. A qubit can also be a 0, and it can also be a 1. But here's the quantum twist. It can be a 0 and a 1 at the very same time. This wonderfully weird feature is called superposition. Picture spinning a coin. While it's up in the air, spinning like crazy, is it heads or tails? You could say it's kind of both, right? A blur of possibilities. It's only when the coin lands, when it stops moving, that it picks a side, either heads or tails. A qubit in superposition is a lot like that spinning coin. It holds the potential to be a 0 and the potential to be a 1 all at once. Mathematically, we write this state as a mix of ket 0 and ket 1. Think of these as the basic quantum states, like our classical 0 and 1. A qubit state, often written as the Greek letter psi, can look like this: alpha 0 plus beta 1. Now, alpha and beta aren't just random numbers. If you square their sizes, absolute value of alpha squared and absolute value of beta squared, you get the probability of the qubit being a 0 or a 1 if you were to measure it. So, a qubit isn't just an on-off switch. It's a whole spectrum of possibilities, a delicate balance of chances waiting for that measurement. This power to be in many states at once is what could give quantum computers their incredible processing power, letting them chew through tons of possibilities in a way classical computers can only dream about. Introducing the Bloch sphere, your qubit compass. So how do we even begin to visualize these qubits, with all their superpositions and probabilities? Just trying to picture alpha 0 ket plus beta 1 ket in your head can get tricky, fast. That's where the Bloch sphere steps in to help. It's a really neat, intuitive, 3D way to represent the state of a single qubit. Think of it like a globe, but instead of countries and oceans, it shows every possible state a single qubit can find itself in. Imagine a perfect sphere. The very top point, the North Pole, stands for the definite state 0 Brach. No fuzziness, no superposition. If a qubit is at the North Pole, it's a 0 period. And the very bottom point, the South Pole, that represents the definite state 1. Again, totally clear. If our qubit is hanging out at the South Pole, it's a 1. Now what about all the other spots on the surface of this sphere? Every single one of them represents a different kind of superposition, a different mix of 0 and 1. Points closer to the North Pole mean the qubit is more likely to be measured as 0 Bra. Points closer to the South Pole mean it's more likely to pop up as 1 Brach. And the equator, that line around the middle, States on the equator, like the well-known plus, ket plus, and minus, ket minus states, mean there's an exactly equal 50-50 chance of being measured as 0 or 1. To figure out a qubit's exact state on this sphere, we use something called the Bloch vector. This is just an arrow that starts at the very center of the sphere and points to a particular spot on its surface. The direction of this arrow, which we can describe with two angles, theta, the angle down from the vertical z-axis, and phi, the angle around the equator in the xi plane, tells us exactly what pure state the qubit is in. So, if you know the direction of the Bloch vector, you know the exact superposition of the qubit. This sphere isn't just a fixed map either. When a qubit undergoes some quantum operation, maybe it gets zapped by a laser in a quantum computer, its state changes. On the Bloch sphere, we see this as the Bloch vector rotating, its tip gliding across the surface to a new spot, showing the new superposition. It's a dynamic visual way to keep tabs on a qubit, making complicated quantum stuff much easier to get your head around. For now, just remember, North Pole is 0, South Pole is 1, and everywhere else is some kind of blend, a superposition, all neatly mapped out. Visualizing superposition, the cloud of possibilities. All right, we've got our map, the Bloch sphere. Now let's put our qubit on it, in all its superposition glory. Picture that Bloch vector, the arrow from the center, pointing to any spot on the sphere's surface. This isn't just some random arrow. Its direction actually tells us the precise probabilities of measuring our qubit as a ket 0 or a ket 1. If the vector points straight up to the North Pole, we said it's definitely 0 Brech. The chance of measuring 0 is 100%, and the chance of measuring 1 is 0%. If it points straight down to the South Pole, it's definitely 1% for 0, 100% for 1. But what if it's pointing somewhere in between? Let's say it's angled towards the North Pole, but not all the way. This means the qubit is in a superposition that's leaning towards the 0 ket. If we were to measure it, we'd probably get to 0, but there's still a chance it could be 1. The closer the vector points to the North Pole, the higher the probability of measuring the 0 ket. The more it leans towards the South Pole, the better the odds of getting a 1. Now, you might have heard people talk about a cloud of probabilities. While a pure qubit state is a single specific point on the Bloch sphere's surface, thinking about a cloud can help you get an intuitive feel for the uncertainty that's there. Before we measure, before we take a peek, the qubit isn't secretly a 0 or a 1. It truly exists in this mixed state defined by its Bloch vector. You can think of this vector as representing not just one state, but the potential to become 0 or 1, with the likelihood set by where it's pointing. This superposition is where the qubit does its thing. It's where it lives, performing its quantum calculations. It's this ability to explore this whole space of possibilities, represented by the entire surface of the Bloch sphere, that's so incredibly powerful. It's a state of pure potential. The qubit isn't hiding its real value. Its real value is this superposition, this particular spot on the Bloch sphere that holds all the probabilities. Think of the sphere as a menu of all possible states, and the Bloch vector as the qubit's current order. An order that has a bit of everything until the waiter, that's measurement, comes along and makes it pick just one thing. The main event, quantum measurement and the collapse. Okay, the scene is set. Our qubit is chilling in a state of superposition, its Bloch vector pointing somewhere on the sphere, not quite north, not quite south, but somewhere that captures a mix of possibilities. Now for the main event. What actually happens when we measure the qubit? In quantum mechanics, measurement isn't like just passively looking at something. It's an active process, an interaction that forces the quantum system to give up a specific answer from its range of possibilities. For a qubit, a common way to measure it is in what's called the z-basis. This basically means we're asking the qubit, hey, are you a 0 or are you a 1? We're making it choose between the North Pole and the South Pole. And this is where the collapse happens. The instant we do this measurement, the qubit's delicate superposition is gone. Poof! That Bloch vector, which was pointing to a particular spot on the sphere showing its fuzzy quantum state, instantaneously jumps, or collapses, to either the North Pole, representing 0, or the South Pole, representing 1. There's no in-between anymore. The cloud of probabilities disappears, solidifying into a single definite point. So, which pole does it jump to? That's where the probabilistic heart of quantum mechanics really shows itself. We cannot, even in theory, predict for sure which outcome a single measurement will give us. If our block vector was pointing closer to the North Pole before we measured, there's a higher chance it will collapse to 0 bra. If it was closer to the South Pole, it's more likely to collapse to 1 briquet. But it's always a probability. If it was right on the equator, a 50-50 state, then it's literally a coin toss which pole it will snap to. Think about our spinning coin again. Measurement is like slamming it down on the table. The spin, the superposition, is gone, and it's either heads, 0, or tails, 1. The really important bit is that after the measurement, the qubit state is no longer the superposition it was in. If we measured it and found 0 ket, its block vector is now pointing straight to the North Pole. The magic of being in multiple states at once is, for that qubit, over for now. It has given us a classical piece of information, a 0 or a 1. This collapse is one of the most fascinating and debated parts of quantum mechanics. It's sudden, it's based on probabilities, and it fundamentally changes the system's state. The block sphere gives us an amazingly clear way to see this. A vector peacefully pointing to one spot, representing a world of potential. Then, wham! With the act of measurement, it's instantly zapped to one of two extremes. The quantum dance gives way to a classical answer. Why does this collapse happen? A glimpse into the mystery. So we've seen the block vector snap, the superposition vanish, and a definite state pop out. The block sphere does a fantastic job of showing what happens during qubit measurement. But the big question, the one that keeps people scratching their heads, is, why does this collapse happen? Why does just looking at a quantum system change it so drastically? Well, that, my friends, is the core of what's known as the measurement problem in quantum mechanics. And it's a topic that's fueled arguments among physicists and philosophers for almost 100 years. The honest truth? There isn't one answer that everyone agrees on. The oldest and maybe most standard idea comes from the Copenhagen interpretation. It basically says that the act of measurement itself is what makes the wave function collapse. In this view, things like a qubit's definite state, being a 0 or a 1, don't really exist in a solid way until you measure them. The collapse isn't something that the normal smooth equations of quantum mechanics describe. It's like a special rule that kicks in when an observation happens. It's just how the universe seems to work at this tiny level. But not everyone's happy with that. Other interpretations offer different ways to think about it. The many worlds interpretation, for example, suggests there's no actual collapse at all. Instead, every possible outcome of the measurement does happen, but each one happens in a separate parallel universe. So, when you measure a qubit and get 0, in another universe, another version of you measured 1. Pretty wild, right? Then there are ideas that look more at the role of the measuring device, or that think of the quantum state more as a description of what we know about the system, rather than what the system inherently is. For what we're doing with the block sphere, the main thing to remember is that while the why is super complex and still up for debate, the what is visually pretty clear. The sphere doesn't solve the measurement problem, but it lets us precisely describe and see the jump from that rich quantum superposition to a single classical outcome. It shows the before and after of this puzzling process. The magic of the collapse, whether it's a real physical thing or something to do with branching realities, is perfectly shown by that dramatic leap of the block vector. It's a great reminder that at the quantum level, reality is a lot weirder and more fascinating than our everyday experience might suggest. If watching that block vector snap to attention has finally made qubit measurement click for you, or at least made it a bit less confusing, do me a quick favor and hit that like button. It really helps the channel out. And if you want more quantum ideas broken down and made clearer, Make sure you're subscribed and have those notifications switched on. Now, I'd love to hear from you. What other quantum mystery, big or small, has you stumped or just curious? Let me know down in the comments. Your suggestion might just be our next breakdown. The Block sphere, demystifying the quantum leap. So there you have it. The Block sphere, helping us get a visual grip on the tricky world of qubit measurement. We've gone from understanding how a qubit can be many things at once, its superposition, shown by a vector pointing anywhere on the sphere, to seeing that sudden dramatic change when we dare to look, the collapse of that vector to a definite north or south, a 0 or a 1. This isn't just some abstract drawing. It's a really useful tool that helps us build an intuition for the basic rules running the quantum show. It turns what can feel like impossible math into something more like a tangible geometric picture, letting us see the shift from that cloud of probabilities to a single solid reality. The mystery of why the collapse happens is still a hot topic, but the Block sphere gives us undeniable clarity on what happens. It helps to lift the fog, at least a bit, around that quantum leap from possibility to actuality, showing us that even the strangest bits of physics can be mapped out and, at least partly, understood. The journey of a qubit, from its rich superposition to its measured outcome, is a fundamental dance of the universe, and the Block sphere is our little window into that amazing choreography.